Hello everyone. In this video, we are going to look at some of the probability stuff that we saw in the slides, but this time we are going to use R. So this script that I have over here will show how to translate that math theory that I showed in a previous video and how to apply that in a more practical sense by computing it. So let's go section by section. I begin by clearing off the template using the rm command. And usually a good practice when you're working with random numbers is to set the seed at a specific number. So I have used 1, 2, 3. You can use any other number. But the purpose of setting the seed, it's very important for reproducibility. It ensures that the random functions will give the same results each time we run the code. Now, it's not super important for the larger results, but it will ensure that you keep getting the same numbers. It won't affect the qualitative nature of the results. If it does, then you're doing something really, really wrong. So let's begin by looking at the counting principles. So the line 15 is a mechanical way of implementing the permutation function. So if I use this function to pick 2 out of 3 and then arrange them, then I will get 6 possible combinations, which means that if I have 3 objects and I want to select and arrange 2 out of them, then I can do that in 6 possible ways. The other line 21 onwards is combinations. So there are 2 options when you're working with combinations. One, and this is usually more preferred, you have the choose function to work with. But you can also code it up manually, as I've done over here, like 23 to 25. And then if I do the same numbers, I want to choose 2 out of 3. I will get 3 possible scenarios. I can just type choose parenthesis 3 comma 2 and I will get the same result. Remember that permutation means choosing and arranging. Combination only involves selection. So in line 36, for example, ways to select 3 people out of 10 is combination 10, 3. And doesn't matter whether you're using the inbuilt function or you're using something that you have coded up yourself, you will always get the same result. So now let's look at the card deck example. So first step would be to define the suits vector. So I have in line 45, I have this name is this vector suits that contains hearts, diamonds, clubs, and spades. I have the values, which is a vector of ace, 2, 3, 4, up to 10, followed by jack, queen, and king. And then I use the expand.grid function in line 47, which creates all possible combinations of suits and values. So I've run line 45. Let's run line 46 and 47. So I have the deck over here as a data frame. So if I click on that, so I have the entire suit. Okay, and this is a randomly generated deck of cards that I will work with. So now the probability of drawing an ace is, as you know, it is 4 by 52. And you can see that it is 0.0769. So if you type 4 by 52, you get the exact same thing. The probability of drawing a face card, which is Jack, King, in, is we first create a vector of the face card, so Jack, Queen, and King, and then we look at the all possible combinations divided by the total number of cards in the deck. And that is 12.2307 E face over here. Another way of looking at that is 12 by 52, which is the exact same thing. So this is how we can manually code up these probabilities. For the die rolling example, first we create a vector called die, which takes the values 1, 2, 3, 4, 5, and 6. And then the probability of rolling a 6 is all possible combinations where the die rolls exactly 6 divided by the length of the die. So the length of the die is 6. Scenarios where die is exactly equal to 6, captured by double equality sign, is 1. So the probability of rolling a 6 is 0.16666, which is 1 upon 6. Probability of rolling an even number, I define that as P even. All possible cases where the rolled number is an even number. And to do that, we typically use this function over here. This means that the die outcome divided by 2 should generate a remainder of 0. So this is how we separate even from odd numbers, and we divide it by the length of the die. And that is exactly 50%. So as you can see, you can play around with the other codes, and you can try out other scenarios on your own as well, and you can match that with the theory to be more familiar with it. From line 81 onwards, we look at conditional probability. For this, the code the code here is a little more complex, and I'm going to work with an example where I will generate a simulated data where men have a 70% chance of exercising regularly, while women have 50% chance. This is nothing to generate controversy, so please do not take this the other way. So the first thing first, so what line 87 does is that it takes a vector comprising of M and F, generates 100 number of observations. Replacement is allowed, because remember, you have to allow replacement because you're basically dealing with two numbers and you have to go over 100 times. And you assign a probability with a vector 0.4 and 0.6. So men are 40% likely to be in the sample. So 0.4 corresponds to M and 0.6 corresponds to F. And then you combine them in using the vector function. So we run lines 87 and 88. We have a character. So let's take a look at that. Okay, it's not ready yet. Sorry, my bad. So now so lines 91 to 97 creates that loop. So what line 91 to 97 does is that for all iterations between 1 and 100, it will first look at the gender of that observation. If it is M, then the corresponding exercise observation will be either Y with a probability of 0.7 or N with a probability of 0.3. Otherwise, that entry will be from a vector of C, Y, N, where Y will be probability 0.5 or N with probability 0.5. So this is what I'm doing over here. First, I'm looking at whether the person is man or a woman. Based on that, I am assigning a vector. I'm assigning a character yes or no with specific probabilities. And once that is done, I'm going to create a contingency table, and I'm going to print that for easier exposition. So this is what it looks like. So in my table, there are 29 women who do not exercise regularly, 31 women who exercise regularly, 10 men who exercise regularly, 10 men who do not exercise regularly, and 30 men who do exercise regularly. So this is consistent with the probability numbers that I've set. If you change the seed number, you will get slightly different numbers, but it will still be consistent with the numbers that we're going to plug in. So now the probability of, I want to calculate the probability that the person exercises, that exercise equals 1. So that is, so that is the sum of all exercise equals 1 divided by the length of the exercise. And that is 0.61. I want to calculate the probability that the person is a man is all possible entries where the gender is M divided by the length of the gender, which is 0.4. And you can check that as well. So 10 divided by 10 plus 30 is 0.4. Exercise equals Y. So 31 plus 30, which is 61. Sorry, exercise is 31. Sorry. So 31 divided by 31 plus 30. Oops. No. So this is my bad. This is not the right way forward. So in order to cross-check whether this entry is right or not, let's take a look at the total number of entries where exercise is yes. That is 31 plus 30, which is 61, divided by all the possible entries under exercise column. So all the no's plus all the yeses. So it's going to be 61 for all the yeses plus 39 for all the no's, and you get 0.61. So this is how we can cross check. Suppose I want to calculate the probability that the person exercises and the gender is male. So P yes and male is all the entries for which the exercise is Y and gender is N divided by the length of the exercise. So this is that scenario. We then implement the medical testing example from our slides, where we have a disease with 1% prevalence, a test with 95% sensitivity, and a 90% specificity. So we set some number. So we set the prevalence at 0.01, which is 1%, sensitivity at 0.95, and specificity at 0.9. So the derived probability is what? P positive given healthy is 1 minus specificity, which is essentially probability that the person tests positive given that he or she doesn't have the disease, so which is 10%. We then calculate the probability of testing positive overall, which is using the law of total probability. So this is the PT given T is the sensitivity times the prevalence plus the other situation where you test positive given you don't have the disease times the probability that you don't have the disease. So because what this captures is the fact that you can test positive in two scenarios. A, you actually have the disease, or B, you don't have the disease. If you have the disease and you still test positive, this is the probability that happens. And if you do not have the disease, yet you still can statistically test positive for that, then the second component captures that. So essentially that's what's happening. So the total probability of testing positive using the law of total probability is 0.1085, which means 10.85% chance that you will test positive regardless of the regardless of your health condition. Now suppose you want to find out what is the chances that you have the disease given that you have tested positive. We do that using the Bayes theorem. So it's basically sensitivity times prevalence. So sensitivity is Pt given D times prevalence, which is Pd, divided by P positive, which is probability of P of T, and that is 0.087. It's often useful to visualize this using the probability diagram. So line 148 sets the canvas. So what it means that I have a margin with the vectors C1, 1, 2, and 1. And I have a plot which is now it's empty. And now I start drawing the branches. So I start the branch D, then D complement, then you test positive given D, you do not test positive given D, you test positive given D complement, and you do not test positive given D complement. So you have all the trees. Now it's time to plug in the numbers. So if we just add all the labels, and just run the codes from 160 to 177, you have all the numbers. So this is what a probability tree looks like. It's often useful to have this and get a better sense of the problem. Then we have multiple events and set operations. Like for this, we need the graphics library. So make sure you have this package installed before you load it. So once it's loaded, I'm gonna write a bunch of lines that will do this for me. And this is what it looks like. So the blue line is the total probability of A. Red line is the total probability of B. And this shaded area over here captures the overlapping section. Then we have that birthday problem, that probability that you share a birthday with at least one person. So the math is there. This is the code for that. So I'm gonna skip the math part, but I would encourage you to look at this, go back to the slide and see what the math is there to try and link that with this. And then we have the codes for the poker hands. So if you have, so the total possible 5-card poker hands is only 2,060,000, and the probability of a royal flush is just 0.00001%. The probability of a full house is slightly better, 0.001. And then we have the expectation and law of large numbers. So we resort to the die roll example. Expected value is all the possible values times its corresponding probability, and it is 3.5. And if we simulate this, suppose we keep rolling the die for 10,000 times, and we create a sample of all the all the outcomes that we get. This is what we see. So the red line over here is the average. As you can see, for very small number of rolls, the expected value is much higher, but then it drops sharply and then remains very close to the average, which is the red line. So this is what law of large number does. If you keep repeating this draw over and over again, then eventually, in theory, your observed average would be equal to the theoretical average. This is the beauty of the law of large numbers.